Welcome to our deep dive into building a zero-to-production agentic stack. In this video, we'll explore how to architect, deploy, and secure a live agentic RAG system using Python's zero-trust principles and Kubernetes. Whether you're an engineer, architect, or tech leader, understanding this blueprint will help you deliver robust, scalable, and secure AI-powered applications. We'll start with the basics, then move through technical details, failure diagnostics, and operational best practices. By the end, you'll have a clear roadmap for deploying agentic retrieval augmented generation in production environments. Let's begin with the technical blueprint for a live agentic RAG deployment. The architecture leverages Python for core logic, zero trust for security, and Kubernetes for orchestration and scaling. This combination ensures that your agentic stack is both flexible and resilient. The blueprint outlines how each component interacts, from user interface to backend orchestration, and highlights the importance of modularity and observability. As we move forward, keep in mind how each layer contributes to the overall reliability and security of the system. Key distinction in modern AI stacks is between standard RAG and agentic RAG. Standard RAG operates as a linear pipeline. A query is retrieved, context is fetched, and a response is generated. Agentic RAG, by contrast, uses an iterative loop. This means the agent can self-correct, retry, and dynamically adjust its retrieval strategy. While this approach increases latency and cost, it delivers much higher accuracy for complex, multi-part queries. Understanding this trade-off is essential for designing systems that balance speed, cost, and reliability. Let's compare the two architectures side by side. Standard RAG uses a single-shot retrieval, which is fast but can miss context or hallucinate answers. Agentic RAG, on the other hand, employs multi-hop dynamic retrieval and includes self-correction and retries. This results in higher costs per query but significantly improves the quality and reliability of responses. The choice between these architectures depends on your application's tolerance for latency, cost, and the need for complex reasoning. No system is perfect, and understanding failure modes is critical for production readiness. In agentic systems, common issues include infinite loops, blind graders, context overflow, and silent quality failures. Each of these can degrade performance or reliability if not properly mitigated. By diagnosing these failure modes early, you can design safeguards and monitoring to ensure your agentic stack remains robust under real-world conditions. One major risk in agentic systems is the infinite loop or latency spiral. This occurs when agents repeatedly call expensive APIs without resolving the query, leading to runaway costs and slow responses. The solution is to set tool execution limits and implement orchestration observability. By monitoring agent behavior and enforcing limits, you can prevent these spirals and maintain predictable performance. Another common failure is the blind grader problem. Here, the language model accepts irrelevant context and passes it to the generation step, resulting in hallucinated or off-topic answers. To mitigate this, use explicit hallucination checkers and relevance grading nodes. These components evaluate the retrieved context before it's used, ensuring only relevant information is passed to the generator. Context overflow happens when too much irrelevant data is stuffed into the model's context window, hiding the actual answer. This can occur with large vector databases returning thousands of tokens. The mitigation strategy is selective forgetting and hierarchical memory routing. By pruning unnecessary context and organizing memory, you keep the agent focused and efficient. Silent quality failures are particularly dangerous. In these cases, the agent returns a healthy HTTP 200 OK, but the answer is wrong due to poor reasoning. Traditional endpoint monitoring won't catch these. Instead, implement trace-level orchestration, which tracks the agent's decision process and flags anomalies before they reach the user. The heart of agentic RAG is the 5-component agent loop. Unlike fixed pipelines, the agent controls execution through logic gates. The process starts with a router that analyzes the query, followed by a hallucination checker to ensure factual grounding. The retriever then generates targeted search queries, and the generator synthesizes the final answer. Finally, the grader evaluates the relevance of retrieved documents. This loop allows for dynamic, self-correcting workflow. Agent loop begins with the router, which determines whether a direct answer is possible or if external retrieval is needed. Next, the hallucination checker verifies that any generated answer is strictly grounded in retrieved facts. If the answer fails this check, the process loops back for correction. This ensures that only accurate, relevant information is used in the final response. Once the router and hallucination checker have done their jobs, the retriever generates targeted search queries based on the router's instructions. The generator then synthesizes the final answer, using only the approved context. This separation of concerns ensures that each step is optimized for its specific role, improving both accuracy and efficiency. Grader evaluates the relevance of retrieved documents. If the context isn't relevant, the agent rejects it and loops back for another retrieval attempt. This self-correcting mechanism is what sets agentic RAG apart from traditional pipelines. It ensures that only the most relevant and accurate information is used to generate responses. Before diving into complex frameworks, it's important to understand the raw Python implementation. At its core, an agent needs robust, constrained primitives to read and search its environment. Functions like list files, grep, and read file provide the foundation for knowledge base mapping, fast searching, and secure file access. These building blocks are essential for constructing reliable agentic systems. List files function uses Python's pathlib, arglob to map the knowledge base without overwhelming the language model with full paths. This approach ensures efficient indexing and prevents unnecessary data exposure. By focusing on relevant files, the agent can quickly locate the information it needs while maintaining security. For lightning fast search, the grep function leverages a subprocess call to ripgrep, a tool built in Rust. This method bypasses hidden files and respects gitignore, ensuring maximum performance and security. Fast, targeted search is critical for responsive agentic systems, especially when dealing with large knowledge bases. Read file function opens and reads raw text, but only after verifying that the path is relative to the note directory. This check prevents directory traversal attacks, a common security risk. By strictly gating file access, you ensure that the agent can't inadvertently expose sensitive data or system files. Memory is a core component of agentic systems. The architecture includes working memory for fast, temporary storage, episodic memory for session continuity, semantic memory for factual knowledge, and procedural memory for learned actions. Each type of memory serves a distinct purpose, enabling the agent to reason, remember, and act effectively. Working memory provides a fast, temporary workspace for the current session, allowing the agent to process information in real time. Episodic memory, on the other hand, stores user interaction history in vector databases. This enables the agent to maintain session continuity and remember previous conversations, enhancing the user experience. Semantic memory indexes the core knowledge base, such as documents and wikis, for retrieval augmented generation. Procedural memory tracks learned tool calling sequences and schemas, enabling the agent to perform complex actions. Together, these memory types allow the agent to know both what is true and how to do things. Unbounded memory can lead to context distraction and increased costs. To address this, apply the RIF formula, recency, relevance, frequency, using Ebbinghaus decay curves. This approach aggressively prunes vector databases, reducing token costs and keeping the agent focused on the most relevant information. Vector retrieval uses embedding models to find semantically similar documents. For example, OpenAI's text embedding 3 large model with 3072 dimensions and approximate nearest neighbor algorithms like HNSW or IVF. While this method is fast and effective for most queries, it can't perform multi-hop reasoning or synthesize facts across disjointed documents. GraphRag takes a different approach by mapping entities and relationships into graph databases such as Neo4j. This method uses LLM ETL pipelines to extract and structure data, enabling verifiable and explainable reasoning paths. GraphRag is essential for domains like healthcare, legal, and finance, where accuracy and traceability are critical. In the orchestration layer, it's important to distinguish between data and decision responsibilities. LlamaIndex serves as the vertical data layer, handling document ingestion and retrieval. LangGraph, meanwhile, acts as the horizontal decision layer, modeling workflows as cyclical state graphs. This separation allows for flexible, scalable agent orchestration. LlamaIndex is purpose-built for RAG, managing the ingestion pipeline and document retrieval. It excels at semantic search, hybrid querying, and connecting language models to private data stores. By centralizing data operations, LlamaIndex streamlines the process of finding and retrieving relevant information. LangGraph is designed for agent orchestration. It models workflows as cyclical state graphs where nodes run code and edges define state transitions. LangGraph supports human-in-the-loop, retries, durable execution, and complex multi-agent state sharing. This makes it ideal for managing the dynamic workflows of agentic RAG systems. Most effective agentic stacks use LlamaIndex for document retrieval and LangGraph for decision-making. This synthesis allows you to retrieve the right data and then decide how to use it, supporting complex, multi-step workflows. By separating these concerns, you achieve both flexibility and reliability. Silent failures are a major risk in AI systems. A hallucinated client name or a misrouted tool call can return a healthy HTTP 200 OK, masking the error. To solve this, wrap LLM calls in retrievable blocks with exponential backoff and set maximum retries. This approach increases observability and ensures that errors are caught and handled before they impact users. Security is paramount in agentic stacks. Zero trust principles restrict what each tool can do, how often, and where. Assume that any agent could be compromised and design your system to contain the blast radius. This means implementing strict controls at every layer from identity to network boundaries. Agents should never share API keys in environment files. Instead, require unique, short-lived, hardware-backed cryptographic identities for each agent. This approach ensures that service-to-service calls are secure and traceable, reducing the risk of credential leaks or unauthorized access. Move beyond traditional RBAC role-based access control to context-aware ABAC attribute-based access control. ABAC evaluates time, data sensitivity, and risk score dynamically, providing more granular and adaptive security. This is essential for modern, dynamic agentic environments. Enforce identity-based isolation and mandatory sandboxed execution for any agent handling untrusted input. For example, use gvisor container runtimes to sandbox agents. This prevents compromised agents from affecting the broader system, maintaining overall security and integrity. Treat all external data as untrusted, including emails and web scrapes. Use constitutional classifiers to scan inputs and reject malicious instructions before the agent processes them. This proactive approach helps defend the perimeter and prevents prompt injection attacks. Agents must operate from an explicit list of permitted tools for each function. Deny by default policies ensure that any invocation of unlisted tools is immediately rejected. This strict allow listing approach minimizes the attack surface and enforces operational discipline. Prevent unscoped privilege inheritance by ensuring that high-privilege agents downscope their context before delegating tasks. This prevents lower privilege agents from gaining unintended access, maintaining strict separation of duties and reducing risk. Design your infrastructure to be immutable, capable of being destroyed and rebuilt in minutes. This approach, supported by tools like Terraform and Docker, ensures that your environment is always consistent, version-controlled, and easy to recover in case of failure or breach. Package your Python environment, including LangChain and LlamaIndex, into a portable Docker image. This encapsulates dependencies and exposes a clean REST API for orchestration. Containerization simplifies deployment, scaling, and maintenance across cloud environments. Replace manual cloud setup with version-controlled infrastructure using Terraform. Automatically provision AWS VPCs, secure subnets, and deploy elastic Kubernetes service clusters. This automation ensures repeatability, security, and rapid recovery. Deployment specs such as deployment YAML ensure high availability by running multiple replicas of the Agentic app across different nodes. This setup provides resilience against node failures and supports horizontal scaling as demand increases. Securely mount API keys and credentials using secret keyref, avoiding hard-coded secrets. Load balancing exposes the agentic workflow to external traffic via managed service endpoints, ensuring both security and accessibility for users. Horizontal pod autoscaling HPA dynamically scales the number of running pods based on CPU utilization. For example, scaling from 2 to 5 or more pods when usage exceeds 70%. This prevents latency spirals during traffic spikes and maintains consistent performance. Let's walk through the end-to-end workflow. The user submits a query via Streamlit UI. Orchestration triggers a LangGraph agent trace. The agent runs in a Docker container managed by Kubernetes, and Zero Trust protocols authenticate tool requests. LlamaIndex retrieves data, and the agent loop generates a grounded response served back through the load balancer. Operational metrics are crucial for managing cost, latency, and scale. Simple lookups cost around 2 cents, while multi-hop queries range from 18 cents to 31 cents. Agentic latency typically falls between 2 and 8 seconds. Monitoring these metrics helps you optimize performance and budget. At scale, costs can add up quickly. For example, 1,000 queries per day can result in LLM API costs of around $2,000 per month for complex reasoning. Understanding these costs is essential for budgeting and scaling your agentic stack effectively. Optimize operations. Implement semantic caching for high-repetition workloads, reducing costs to near zero. Standard RAG operates in under a second, while the agentic loop trades speed for accuracy. Use model tiering, fast, cheap models for routing and grading, and frontier models for final generation. The most successful AI deployments are built on strong fundamentals that withstand scale, drift, and breach from day one.